It's my pleasure to welcome back Peter Behroozi. He visited us about a year and a half ago, also online, unfortunately. So I was just saying to him, we'll have to bring him back again a year and a half from now so he can visit us in person. We'll surely be in person by then. But it's great. It's always great to hear what Peter has to say. So he's got quite the pedigree. He got his bachelor's from Harvard in 2006, and then did his PhD at Stanford with Risa Wexler, finishing in 2012. And then he did postdoctoral work at Stanford Space Telescope and Berkeley, where he held a Hubble Fellowship. And he moved to Arizona in 2017, where he has been since. So Peter has an impressive body of work. He's done lots of things, and he's made enormous contributions to our understanding, in particular, of galaxy evolution, how galaxies that we observe are linked to the dark matter halo structures that we get from numerical simulations. And he's got, I think, some of the most comprehensive and useful, I think, models out there that allow us to link those two things together and make predictions for future surveys and to interpret all the work that we are doing. So it's been an invaluable contribution to those of us working on galaxy evolution. And so he's going to tell us, I believe, about the latest incarnation of his work there, and linking in particular supermassive black holes to galaxies and the dark matter halos in which they live. So with that, I welcome again Peter Behroozi, and please take it away.
Thank you so much, Michael. It's always a pleasure to come back to a place that I've given a talk before. It means I've done something right. So let's see if I can tell you now about what I've been most recently up to. So that's, as Michael said, that is trying to understand the evolution of supermassive black holes. This is work that's been mostly done by my graduate student, Hao-En Zhang, but also in collaboration with lots of other fine folks, Marta Valenteri, Joe Silk, Xiaoyi Fan, Phil Hopkins, Junyi Yang, and James Aird. So, right, so let's start with a little bit of motivation. I don't need to motivate studying black holes too much to astrophysicists. They're some of the most interesting and mysterious objects out there. Just a couple of words of context, though, so we know that there's an event horizon around black holes. And that means when we observe a black hole, at least classically, no information or light can come out of that event horizon. So we can see how the black hole is today, but we can't recover how it was, say, a year ago or a billion years ago, or at any other point in its history. And so that's my interest, is I want to understand how supermassive black holes form and grow in galaxies. And when I say a supermassive black hole, I mean a black hole that's greater than 100,000 times the mass of the sun. Okay, so I hope to make it a little bit less mysterious to you after today, how we can recover histories of black holes, at least statistically, on an ensemble average. Why else do they matter? So supermassive black holes are found at the center of basically every galaxy we can see. And sometimes they have very dramatic effects. So this is a particularly dramatic example from Sun A, where if you look in the optical, that's sort of this panel down here. If you look in the optical, what you find is an elliptical galaxy with a dust lane that's warped, possibly a recent merger that's happened here. But if you look in the radio, you see these huge jets of energy coming out from the center of the galaxy. And if you look in the X-ray, you see that these jets are driving lots of hot gas outward in sort of these X-ray bubbles like that. And so the summary, the physical story that's happening here is that there's a supermassive black hole in the center of this galaxy that's accreting matter. And as that matter accretes onto the black hole, it heats up, drives these huge jets of energy, and heats up the surrounding gas. And the amount of energy released is so great that it's able to eventually at least quench star formation in this galaxy, prevent it from happening, so that no new stars, no blue stars can be forming in this galaxy while this sort of feedback is happening. And this is nuts. To give you a sense of the size scales involved, and this is an analogy I owe to Martin Elvis, the size of the supermassive black hole, the physical size of the supermassive black hole in the center of this galaxy the ratio of that to the size of the galaxy itself is like the ratio of the size of a spot on a ladybug's back, the size of the entire Earth, right? So it's as if something on the back of a ladybug could release so much energy that it could wipe out humanity on the entire Earth. And that's what's happening in this galaxy here. That supermassive black hole is sort of wiping out star formation across the entire extent of the galaxy here. So that's sort of why it's important to study black holes for galaxy formation, also sort of why it's interesting from a physical perspective to know how supermassive black holes form. So I want to solidify these sort of vague interests into more concrete questions. Let me give you a little bit more context about what we know about black holes. We know that there's a relationship between the mass of the black hole and any of a variety of proxies for mass of the galaxy. So this happens to be velocity dispersion of the bulge. You could also look at the mass of the bulge or other properties. But the main point is that the larger the galaxy, the larger the black hole, and there seems to be a reasonably tight correlation between the two. We can only measure this without a lot of systematics or selection effects at redshift 0. We still have a decent amount, but of course, it gets even worse as you go to higher redshift, where you can't find black holes unless they're sort of spewing out lots of energy. We know from looking at growth rates of black holes and growth rates of galaxies that the two seem to track each other over time. So on the bottom axis here is redshift. So higher redshifts, of course, that means further back in the history of the universe. If we look at the average growth rate of black holes, so the cosmic black hole accretion rate, that's this black line, that's basically proportional to the rise and fall of the cosmic star formation rate. Those are these blue points divided by a factor of about 10,000. So the growth of galaxies and black holes seems to track each other, but that's not good enough to say that this relationship holds at higher redshift, because there are many ways that you could construct black holes and galaxies growing at the same rates on average, or the sum over the entire cosmos, whereas this relationship looks different, has more scatter, or it has a different slope over time. So the first key question is, how does the mass of the black hole and its growth rates depend on the properties of the galaxy that it lives in and the cosmic time, or the redshift? The second question is related to recent discoveries. So my colleague Xiaoyi Fan and others have been discovering, it seems, every year another supermassive black hole that's sort of too big too early. And so what does this mean? When you have a black hole, you of course can grow it by adding matter to it. But every time you add matter to it, you release some energy as radiation. And when you release energy as radiation, that gives you radiation pressure, which sort of balances the force of gravity that brings material in. And because both radiation pressure and gravity fall off from the black hole as 1/r², 1 over the distance squared, if you have enough matter falling in, then the radiation pressure can be sufficient to balance the force of gravity for material falling in, so it won't try to fall in any faster than it already is. You can work out what that limit is on the growth rate for a black hole under a couple of assumptions. So the common assumption is sort of steady state accretion and spherical accretion. And if you make those two assumptions, then the maximum growth rate for a black hole is something like this. So the Eddington ratio, the Eddington rate, as it's called, or Eddington limit, is the mass of the black hole divided by a characteristic time scale of 50 million years. And if you work out what that means for a black hole that starts out, say, at 100 solar masses at the Big Bang, or close to it, then the maximum mass you can reach by redshift 7 is about 10 to the 8.5. And so if you find something like a 1.5 billion times billion solar mass black hole at above redshift 7, that's what people are saying when they mean, oh yeah, it's too big too early. You can, of course, get around this Eddington limit. For example, if you have non-spherical accretion, which we think happens if you have accretion on a disk, of course, that means the radiation pressure isn't as efficient at preventing infall. Or if you have non-steady state accretion, that you can also sort of break that Eddington limit. But the larger question remains, that is, why do black holes at this early time know about the Eddington limit or are able to stay at the Eddington limit or slightly above for long periods of time? So the second question is sort of, why do supermassive black holes grow so quickly in the early universe? How does the galaxy and the rest of the universe know to feed them at the right rate so that they can get that big that quickly? Okay, let me pause here before I get to how I'll answer these questions to ask if there's sort of any questions or clarifications so far.
Could I ask how common are these kind of black holes in early universe? High redshift?
So these ones like this, the ones that are too large too early, they're super rare. So in a survey like Sloan, which covers say approximately an order of 10,000 square degrees, so a quarter of the sky, then you might find a handful of these. And so they're rare, but they exist. And so the question is, why do they exist?
Mm-hmm.
Great, any other questions?
So how do we know how massive they are? Or is the argument a little circular? Isn't that based on assuming they're accreting at the Eddington rate? So do we really know that they're that massive, or is that?
Yeah, that's a great question. So there's sort of two arguments that you can make. One argument is you can look at the luminosity and say, well, what if it's accreting at the Eddington limit? Then what's its mass? That's sort of one kind of limit you can put. So if it's accreting at less than the Eddington limit, then its mass is going to be greater. If it's accreting at more than the Eddington limit, which some people think is not possible, then its mass would be less. And so there is an uncertainty there. More commonly, though, what people will do is they'll use a kind of virial argument in which they'll take the width of an emission line and then multiply that by a scaling factor that effectively infers the sort of radius of the broadline region, given the luminosity of the black hole, using relations that are calibrated at lower redshift. And they'll use that to estimate the black hole mass. And both types of estimates tend to agree that the black holes are likely larger than the limit that you would expect from Eddington limited accretion. So there is some uncertainty there as to whether they're really that massive or not. And especially because they're rare, you might expect that, oh yeah, sometimes you'll get errors in these approaches that will make you like that massive. So you're sort of getting at sort of layers of the solution by asking that question.
Well, thanks very much. That was a nice answer.
Great. Okay, so let's continue on. Let's talk a little bit about what kind of observations are available. The basic thing is that there are tons and tons of black holes that you can observe because there are tons and tons of black holes that are growing. And so in surveys like Sloan and surveys like DESI and Boston and so on, we've collected millions of accreting black holes throughout the entire history of the universe, up to very high redshifts. But this is a sample with very large selection effects, right? Because you can only see the black holes that are accreting. You can't see black holes in every galaxy. And when black holes are accreting rapidly, that is when you can see them. Very often it's difficult to see the galaxy behind it because the black hole is accreting so rapidly. In other words, it will outshine the galaxy that it's living in. So only in sort of rare circumstances can you see both the accreting black hole and the galaxy that it's living in. And so there's lots of selection effects that are happening in all the sort of images that we have. The other thing is that we have lots of images of galaxies. So at low redshift, for example, from Sloan, but then also higher redshifts from Hubble and hopefully soon James Webb. We again have millions of images of galaxies at all different redshifts. And these are also interesting because we can use these to sort of piece together a history of the universe in terms of galaxy formation. I'll talk a little bit more about that later. The main point is we have millions of observations of both black holes and galaxies. Each have their sort of unique selection effects, but we have at least lots of information about both classes of objects. And so what I'll do with that information is I'll combine it, I'll try to self-consistently combine all this information to come up with physical models. And the underlying point is that the universe, there's some physical rules that govern how the universe evolves, how galaxies and supermassive black holes evolve. And all observations are consistent with those rules. So any physical model that we dream up must also be consistent with all of those available observations in order for it to be correct, right? And that really limits the space of allowed models that can be consistent with all available observations because we have so many millions of observations. So if we can simulate the selection effects, if we can simulate how the universe would appear for any given physical model, we can test, is it correct or not? And the universe has such great constraining power that's given us with all these millions of observations of both supermassive black holes and galaxies, that only a very, very limited range of models would be allowed to match everything, right? So the analogy that I like to make is an empirical model that you all know and love for the growth history of the universe, right, as a whole. So you have something that's called dark energy, you have something that's called dark matter. We have no idea what either of these things are. We just know that some combination of those describes the growth of the universe. And if you combine different types of observations, in this case, 3 different types, sporadic acoustic oscillations, cosmic microwave background, supernovae explosions, then you get a very tight constraint then on what is allowed in this empirical model to describe the growth history of the universe. And so the same thing is true for galaxies and supermassive black holes. If you combine lots of different observations, then you get very tight physical constraints on how galaxies and supermassive black holes can evolve and co-evolve. Let's talk about how this is done. Supermassive black holes live inside galaxies, and galaxies live inside dark matter halos like this. What is a dark matter halo? It's a region of dark matter that's self-bound and virialized and gravitationally collapsed, we often like to say. And sort of that, what that means is that this is a gravitational potential well in which lots of gas collects. That gas sort of cools, forms a disk, and inside that disk, there's a galaxy that forms. Inside the galaxy, there's that supermassive black hole. So to model this empirically, we can take this apart. So we can split this into a dark matter halo here, and then there's a galaxy that lives in that halo, and there's a black hole that lives in that galaxy. And then the relationships, like a stellar mass, halo mass relationship that describes how galaxies relate to halos. And then there's another relationship, like a black hole mass, galaxy mass relationship, or a black hole mass, bulge mass relationship, if you're an expert, that describes how supermassive black holes live inside galaxies. And the real universe knows what these relationships are, and all observations are consistent with the real relationships. And so then it's our job to figure out what these relationships are between the galaxy and the halo and the supermassive black hole and the galaxy. Okay. So let's talk about the dark matter halos first. Dark matter halos are actually, surprisingly, perhaps the easiest to simulate. And the reason for that is that the motion of dark matter depends on gravity. We think basically gravity alone. Gravity doesn't care about what is the mass, it only cares about how much of it is there in the universe. And so we can put how much dark matter there is in the universe. We can put in sort of what are the density fluctuations in that dark matter from the CMB. And then we can turn on gravity and let a big computer figure out what happens. And what happens is that sort of the material is more smeared out at early times, and then gravity pulls it together to form lumpy objects, clumps like this that are self-bound and collapse. Those are halos. Those objects continue growing by accreting matter from their surroundings and merging together to form sort of larger and larger and larger objects over time. And sort of each of these bright points of light represents a different dark matter halo. And at the center of each of these dark matter halos, you'd expect baryons to collect and form galaxies. I'll let that play for a little bit in case there are any more questions. about that. Okay, so what can we get from a dark matter simulation? We can get a couple of things. So we can measure, for example, how many dark matter halos there are of a given mass. And we can also measure how they grow over time. So just to summarize that, we can look inside the simulation region and see how many objects there are as a function of how big they are and the age of the universe. You can just count how many collapsed objects there are. Yeah, is there a question?
I don't see one.
Okay. And we can also track objects through time. So if we, for example, look at objects that are a certain mass at redshift 0, the present day, we can track how big they were as you go back in time and sort of recover what are typical accretion histories or growth histories for dark matter halos. So that sort of sets the anchor. So we know how gravitational potential wells in the universe grow and merge over time. So if we have some relationship between, say, the mass of the galaxy or the growth rate of the galaxy and properties of that dark matter halo, then we can populate the dark matter halos with galaxies and estimate how that universe would look like. Right, so let's walk through that. If we start with the dark matter simulation, that tells us how many halos and how massive they are at a given time, as well as how those halos grow throughout time and merge with other halos throughout time. So you can sort of construct a growth tree or merger tree of the history of halos throughout time. We then put in a model for how galaxies form where the star formation rate is related to halo properties like the halo mass, mass accretion rate, and redshift. We can then ask or calculate how do the galaxies in these halos grow. So if we start out the first redshift, put in a certain amount of stars given the star formation rate, and then keep on adding stars according to this relationship, we can construct for any model here, how do galaxies grow within dark matter halos. And we don't need to limit ourselves to models that we think a priori are physical. We could have any mathematical relationship here for like a collection of splines or a 3D grid or anything like that for how does star formation rate relate to these three halo properties, true halo properties in time. Because we can just calculate how do galaxies fit into halos for any relationship here. And the nice thing is that there's so many observations that even if we start from a space of models that includes really unphysical ones, the observations limit us then to saying only the models that match all the constraints, all the observations are the ones that could be plausibly physically correct, right? So we don't need to start with many assumptions here. This could be a very flexible functional form, but the number of constraints in the real universe means that we end up still with the right physical model or close to it if it matches all observations. Right, so if we put in a dark matter simulation, if we put in galaxies as a dark matter simulation, we can simulate then what the universe would look like for any model that we pick here. We compare that to the real universe and we do an MCMC, repeat this over and over again, generate billions, sorry, not billions, but millions of new models to then see which ones end up matching the real universe and take a look at those. This almost seems like magic, right? So the main point is that we know that there's some underlying relationship between the rate of formation of stars in a galaxy and the properties of its halo. And we just then want to ask the universe, what does that look like? And so an MCMC solves that inverse problem for us. It inverts out what is that underlying star formation rate relationship given all the constraints that we see. And so here's an example of a trip through the universe machine, a trip through one of these mock universes that looks more or less like the real thing. And the point of this is to say that we can combine many different types of observations about the real universe. So for example, number counts of galaxies as a function of their mass and time, or clustering of galaxies, or weak lensing, or even higher order statistics like how many groups or clusters of galaxies there are. Sort of any statistics that you can imagine calculating for the real universe that might tell you about things like what is the halo mass or mass accretion rate in the halo. You can then also use those to constrain how do galaxies and their star formation rates relate to those halo properties. So the conclusion from that is that you can back out relationships between galaxies and halos. And so this is a now classic plot that shows as a function of the mass of the halo down here, and you can see different mass scales like dwarf galaxies, Milky Way-like galaxies or clusters. What is the sort of ratio of stellar mass to halo mass? How much of the matter within the halo has turned into stars in the central galaxy? You see this characteristic shape where things are more efficient in Milky Way mass halos, are turning the available gas into stars than they are at low mass or high mass halos. But that's a little bit besides the point. So the main point here is that you can recover relationships between galaxies and halos by using this type of forward modeling approach, coupling a guess for how galaxies fit into halos with an MCMC to try many different guesses. Any questions about putting galaxies into halos?
So in these approaches, do you optimize for number of parameters? Right. I could imagine you.
I'm so glad you asked this question. You want to optimize for flexibility to start with. And the reason for that is that you have a huge number of constraints coming from the universe, so you could constrain a ton of parameters here. And the reason that you would want to constrain a ton of parameters is that when you start with fewer parameters contains an assumption then about the available physics the universe could draw on to form galaxies. And the more parameters that you have, then the weaker those assumptions become. And so the more parameters that you start with, as long as you can constrain all of them, that's good, because then you can discover physics that you didn't know previously existed. But then you want to go back and ask, how many parameters could I get away with to describe the same sort of evolution of galaxies? So then you can get closer to what is the underlying physics. That is there a parameter of fewer is there a model with fewer parameters that can describe the same universe or not?
James has a question as well.
Great.
Oh yeah, I was just going back to the stellar to halo mass plot.
Yeah.
Do you want to just talk briefly about the two ends of that?
Sure.
Why is there disagreement between all those results at the massive end and at the low mass end? What do you think those are?
Great. Yeah, so at the massive end, there's a big mess, and Michael knows a lot more about this than I do, in terms of actually measuring the stellar mass of galaxies. And so if you look at the galaxies that the BCGs or the various central galaxies and clusters, they have a very extended stellar envelope, and it's very, very difficult to measure total mass because you have to do all kinds of subtraction, you have to do all kinds of cutouts of other galaxies, and there's lots of sort of disagreement about that. You'll notice that between this purple line, which is the most recent results, and say one of the older lines, like this black line, the methodology is basically the same between these, and then all that changed was how do we measure the stellar mass of bright galaxies.
Mm-hmm.
At the low mass end down here, what happened is that some of these are extrapolations. Some of these assumed a parameterization that was probably less correct as you go to lower and lower masses here. And so there's sort of a combination of those two effects, which is explaining sort of this scatter here. And this red line here, which is my work from 2013, that's wrong because it assumed a correction to the low surface brightness galaxy counts that turned out to be incorrect.
Mm.
So there's a fear sort of maybe a decade ago that we weren't accurately getting in Sloan the correct number of low surface brightness galaxies. There's some incompleteness there. And so this assumed a correction for that. But then more recently, we found that it's more likely to be a lower number of galaxies and that Sloan wasn't too far off.
Okay, thanks.
Great. Okay, so I'll skip a little bit some of the other discussion about what we can learn from putting galaxies into halos, because I do want to get into black holes. So I'll then talk about how do we extend this framework to get into black holes. And the idea is very similar. So if we start from a dark matter simulation and we have some way of putting galaxies into those dark matter halos, then all we need on top of this to get black holes is some way of some parameterization for how do we put black holes into galaxies. And the concept is exactly the same. So if we have some guess for how black holes fit into galaxies, in this case, a probability distribution for their accretion rates. If we have some guess about how black holes fit into galaxies, then we can put black holes into those galaxies that live in the same dark matter simulation, and then predict what would we see for all the galaxy properties, as well as all the supermassive black hole properties that we can conceivably observe. And again, because we have a mock universe, we can apply the same selection effects in the mock universe as are applied for real life observations. Okay, so in other words, we generate again a mock universe, we measure that mock universe both for the statistics of galaxies as well as for black holes, and we do an MCMC to explore a very flexible parameter space for both the star formation rate of galaxies as a function of halo properties and the relationship between black hole properties and their host galaxy properties here. And the data that goes in is important because the more data that goes in, then the better constraints that you get. So just like for cosmology, the more different types of observations you combine, the tighter the constraints on omega matter and omega dark energy. The same is true for physical models of galaxy and supermassive black hole formation. So on the galaxy side, we have lots of things. These are already the same that went into the universe machine that relates galaxies to halos. Things like stellar mass functions, star formation rates of galaxies, quench fractions of galaxies, luminosity functions, and a few more. For black holes, what goes in are sort of, again, many different things. So there's the relationship between black hole mass and galaxy bulge mass at redshift 0. And this sort of sets one anchor point for how big can black holes get in galaxies. There's another relationship in terms of how many growing black holes are there as a function of time and how bright they are. And these are called quasar luminosity functions, and they basically tell you how do black holes grow over time. They don't tell you which black holes are growing, but they tell you sort of what is the distribution of accretion rates and what is the overall cosmic growth rate of black holes. We also have information, so these are X-ray, AG, and occupation fractions. What does that mean? That means how frequently do you find growing black holes in galaxies as a function of, say, the galaxy's stellar mass and how bright the black hole is down here. And this tells you information about the distribution of accretion rates for black holes in a given galaxy stellar mass range. And if there's a relationship between black holes and galaxy mass that continues beyond redshift 0, then this constrains sort of how black holes of a given mass can accrete. And the reason that you can get those constraints at all is because you need self-consistency. So in other words, if you have a black hole of, say, mass 10 to 8 and a galaxy of mass 10 to 11 at redshift 1, you can look up what is its growth rate from redshift 1 to redshift 0 and see, does that end up matching the constraints at redshift 0 for how we know black holes live in galaxies. So this is a very important anchor point because combining this constraint with sort of growth rates of black holes in galaxies as a function of stellar mass lets us constrain what is sort of typical black hole masses or what are typical black hole masses in galaxies as a function of time. And then the last bit of information are active supermassive black hole mass functions. These are sort of an estimate of black hole masses, again, subject to the same concerns that were raised earlier in the talk about how do you measure the mass of a black hole, especially at high redshift. But within sort of a factor of 5-ish, they tell you how massive are black holes at a given redshift. And that gives you constraints on how much the radiative efficiency for black holes can vary as a function of time. And so the Trinity model then combines three things. It combines dark matter halos, it combines galaxies, and combines supermassive black holes all into one package. What I haven't shown are the parameterizations for all the nuisance parameters that control systematics, like how wrong are the masses that you get in supermassive black hole mass functions, or how wrong are galaxy stellar masses that you measure at, say, redshift 5 compared to redshift 0. Things like that are important, but I haven't shown them here. And so what I want to get to then are some of the results that come out of this model. So what we've done is sort of constructed models that are then consistent with all these different types of observations, all these black hole observations, as well as galaxy observations. And so what is the range then of models that are consistent with all these data? The first thing that comes out is that the black hole mass galaxy mass relationship doesn't change a whole lot with time. So you see some evolution here, maybe like a factor of 2-ish, but overall, the sort of general shape and structure of this is pretty similar at redshift 0 as it is at higher redshifts. What does that mean in terms of physics that you can learn from this? What that means is that if you look at different simulations, so these are different hydrodynamical simulations, which try to simulate from first principles. You have dark matter, you have baryons, you have some recipes for how baryons combine to form stars and how baryons accrete onto black holes. And it looks like for each different simulation, there's sort of a different path of evolution for the black holes over time for a fixed galaxy mass. And then what we can do is we can turn around and say which of these different paths are plausible given the constraints from the real universe. And so things like maybe TNG 100, that's a new version of Lustrous, or the Eagle simulation, or maybe the Sima simulation, they seem like there's somewhat less evolution here, and that would be consistent with what we find. Whereas some of the versions with more evolution, say the original Lustrous or Horizon AGN, maybe somewhat less consistent with what we find. That is, they're less consistent with the available observations in the universe. And so what that means is that certain physical recipes, as opposed to sort of the flexible functional forms that we put in here, certain physical recipes can be ruled out just by asking, do you get the same evolution in black hole mass that's required to match all the observations?
I guess your models also tell you, if you go back to the previous diagram, how an individual galaxy black hole pair evolves in this diagram. I don't know if you're going to come to that or not.
Yeah, so it tells us a little bit about that. We can, for example, get average growth rates or average growth histories of black holes, and that can stretch as far back as we have observations. I'm trying to think if I included
a plot. For example, you know, to ask a specific question, at the high mass end there, is that evolution is mostly coming because the stellar mass is, you know, the black holes are mostly constant in mass, but the stellar mass is going up, so galaxies are moving.
Oh, great, yeah.
To the right.
So yeah, so most of the evolution here is coming from the growth of the bulge, as opposed to you don't lose mass in the black hole, right? So most of this here is coming from the growth of the bulge, and the black hole is growing too, but at a sort of much slower rate.
Mm-hmm. Yeah. Okay.
Yeah,
and that's great.
Sorry, I had another question. So I'm a bit confused here. So these simulations, they have all the baryonic and AGN physics in them. So in principle, you could just compare their predictions with observations. So why do we need this universe machine in between?
Great. So you could compare all of these with observations, but it's much faster if you don't have to. So if you already know at redshift 5 that your black hole mass stellar mass relation is not looking right, then you can already fix the recipe, because it's much less expensive to run to redshift 5 than to run to redshift 0 and find, oh no, I don't match now the redshift 0 like distribution of luminosities in black holes. But if you can find that out by redshift 5 or even earlier, that there's something wrong, then you can be much more efficient in fixing the recipe for black hole growth.
Can I ask how you measure black hole masses at high redshift, and when you're considering growth rates, are you only considering radiation? What about mechanical energy, which can exceed radiation in many of these? That can throw things off quite a bit.
Right. So how are black hole masses? So the only sort of constraints, observational constraints that contain black hole masses at higher redshifts are these active supermassive black hole mass functions. And these are all single epoch virial masses. So meaning, of course, that they use the width of a broad line and a luminosity radius relation for the radius of the. So there are problems with that. As I mentioned, maybe a factor of 5, it could be wrong. But that's what it is. And we have nuisance parameters to sort of help include the uncertainty in these masses. There's a second part to your question. Can you ask that again?
Yeah, you're considering only radiation. But what about mechanical energy, winds, kinetic energy?
Yeah. So we've mentioned only radiation, but we actually are using a formula for the so there are a couple of things here. So there's both kinetic energy and radiation that's produced in our models, and so we have sort of an estimate of how much radiation versus kinetic energy, and especially for black holes that accrete now I'm trying to remember which way it goes. I want to say at lower Eddington ratios, most of that ends up in kinetic energy as opposed to luminosity.
Right. Okay. Thank you.
Yeah. And so that's sort of most important at these very low luminosity ends here for these galaxies and black holes.
Yeah, I just wanted to comment that some observation, even of highly quasars that say redshift of 2 can have a substantial fraction and even more of their energy coming out in radio jets than from stuff, radiation coming from the accretion disk. Yeah. And it can have a bigger impact on the surroundings as well. So
that absolutely contributes to errors in these masses. So yeah.
I'm not trying to ruin your day, but it's just something to sort of throw into the mix here, which could change that. When you're excluding certain models, that's something that one wants to keep in mind.
Yeah, and so that sort of goes into the uncertainties here. What we ended up doing is concluding that the simplest thing to do was assume a fixed rate of efficiency with redshift, and then the active supermassive black hole mass functions become redundant. So if you know the distribution of growth rates of black holes, you know the redshift 0 supermassive black hole galaxy relationship, then you can basically back out like what is the offset or typical offset that you need to match these active supermassive black hole mass functions. And so it ends up not being terrible, again, within a factor of 3-ish, but they're not perfect.
Thank you.
Great. Cool. So another thing that I wanted to talk about was sort of how does the mass of the supermassive black hole relate to galaxy formation? And so what I'm showing here is the relationship between supermassive black hole mass, average supermassive black hole mass, and halo mass. So halo mass is on this axis, and some signposts like clusters are up here, Milky Way masses are down here, dwarf galaxies down here. On this axis, you then have redshift, if you prefer, look back time, so early universe, late universe. And this yellow dashed line shows you sort of where do galaxies stop forming stars. So above this line, most galaxies that live in these massive halos are quenched, stopped forming stars. And most galaxies down here are continuing to form stars. And what you notice is that this line seems to have nothing to do with the mass of the black hole. There's no sort of sharp discontinuity here, any sign that it's at a fixed black hole mass. It's not parallel to lines of fixed black hole mass. And so the conclusion from this is that there's no sort of threshold black hole mass above which you stop forming stars in the galaxy. If we look instead at the growth rates of black holes, so if we look at the specific growth rates of black holes, meaning the accretion rate of the black hole divided by the mass of the black hole, and we express that in units of the Eddington growth rate or Eddington limit. So a growth rate of 1 corresponds to growing at the Eddington rate. Then we do find a sharp distinction between sort of galaxies that are quenched and galaxies that are forming stars, because the black holes are growing much more slowly relative to their mass in these massive halos with quenched galaxies, and they're growing much more rapidly in these low mass halos with star-forming galaxies. And so the conclusion from this is that whatever is stopping star formation in galaxies is also stopping the growth of the supermassive black holes. We can't conclude that there's causation there. For example, we can't conclude that supermassive black holes are causing both a decrease in the star forming fraction as well as a decrease in their own growth rates. But we can at least say that there's a strong correlation between the black hole growth rate and the galaxy growth rate here. Another interesting thing about this plot is if you look in the bottom right corner here, the growth rate of supermassive black holes approaches the Eddington limit. And where is that coming from? So if you look at
Sorry, just before you go there, I can't remember if you said this or not, or I missed it. So the correlation between the AGN downsizing and the galaxy downsizing, was that built into your model or not?
No, absolutely not.
Because you had the black hole mass being a function of something, but I didn't know exactly what it was a function of.
Yeah, so the growth rate is a function of the galaxy mass.
The stellar mass.
But yes, the stellar mass. In practice, in the model, we have another piece for how to connect stellar mass to bulge mass that I didn't talk about.
Okay.
So it's implemented as a correlation between the black hole mass and the bulge mass.
Okay, but then isn't it then built into the model in that sense? Because if a process stops the star formation, hence stops the bulge mass from growing, then it necessarily stops the AGN from growing.
So it's difficult to say whether that's built into the model or built into the universe, right? Because at the end of the day, we need to get a relationship that looks like this. So in other words, if the black holes can grow much faster than the bulge, what would happen is the black hole mass bulge mass relation would curve up like that, right? And because it doesn't, then in the real universe, you're limited in terms of how much the black holes can grow relative to the galaxies. And you're then forced to get this type of picture where the black hole growth stops at the same time that the galaxy growth stops.
At some level, sure. Yeah. Okay.
So in other words,
in the highest mass galaxies, that there is a bit of an upturn, in that the masses of black holes are higher, but there are very few of the biggest galaxies, because they have low central surface brightness. It's very hard to measure black hole masses, but I know Lauer many years ago showed that the black hole masses are high compared to the stellar masses in brightest cluster galaxies. So that may actually happen a bit. Maybe that's changed though since then. Maybe, I don't know.
Right. So what I haven't shown here is sort of the growth rate of the black hole relative to the growth rate of the galaxy. So both black holes and galaxies grow at slower rates in these massive halos. Let me see if I have a plot of that handy. Yeah, and unfortunately don't in this set of slides, although it's in the paper, I think. Basically, if you look at the ratio of the growth rates of the black holes to the growth rates of the galaxies, the black holes are growing faster relative to the galaxies in these massive halos. So that would be consistent with the Lauer results. But in terms of the overall growth rates of black holes and galaxies, both go down as you go to later times and more massive halos.
Okay, right. Thank you.
Great. Yeah, so I'll just talk about this piece down here and end and ask if there are questions, because I think I'll otherwise go over time. So what's happening down here with Eddington ratios close to 1 or black holes growing close to the Eddington limit? What's happening is that the relationship between black hole mass and halo mass, or black hole mass and galaxy mass, isn't changing so much. And the galaxies, as well as dark matter halos, are also growing at the Eddington limit for black holes at these early times. So what do I mean by growing at the Eddington limit? So the Eddington limit is sort of a limit on the specific growth rate of a black hole. So the accretion rate of a black hole divided by its mass has units of inverse time, and that basically a limit of 2 times 10 to the minus 8-ish inverse years corresponds to e-folding time of around 50 million years for a black hole. So the specific growth rate limit imposed by the Eddington limit on a supermassive black hole is sitting around here, around 2-ish times 10 to the minus 8 per year. You can also measure specific growth rates for galaxies or for supermassive black holes, for dark matter halos. So for a galaxy, it's called the specific star formation rate. It's basically the star formation rate divided by the stellar mass of the galaxy. And you can observe that. That's an observable thing. In other words, you can measure the stellar mass of the galaxy, you can measure its star formation rate based on the colors of the galaxy. And what you find is that going back to early and earlier times, the galaxy specific growth rates are closer and closer to this limit of around 2 times 10 to the minus 8 that corresponds to the Eddington limit for a supermassive black hole. So you can also look at the growth rate for halos in simulations, which is driven purely by gravity in lambda CDM. And that also is getting higher and higher and higher towards earlier times, because the universe, of course, is denser and and the regions that collapse are rarer and rarer peaks in that universe. And so what you find is that in lambda CDM, dark matter halos are growing at a rate close to the Eddington limit for supermassive black holes. That's pouring on baryons to the galaxy at a rate corresponding to about the Eddington limit. And that means that the black holes had better also grow at the Eddington limit, or close to that. Otherwise, there's just material piling up and piling up and piling up on them that's sort of like waiting to fall in. And so the summary of this picture is that dark matter halos and galaxies in the early universe grow at about the Eddington limit for supermassive black holes. And then black holes presumably can use that material. Maybe the accretion is not spherical, maybe it occurs in a disk, and so the Eddington limit doesn't necessarily need to apply. But whatever it is, the growth of supermassive black holes in the early universe is driven by the growth of their halos and galaxies. And that's why you tend to see the supermassive black holes, or the 2 large black holes at early times, like up to redshift 6 and 7, because that's when you're sort of closest, the galaxies and dark matter halos, that's when they're closest to growing at the Eddington rate. Whereas at later times, and they're much farther away, like an order of magnitude away, so you never hear about overmassive black holes at redshift 2, only at the early times when the host galaxy and host halo are growing at close to the Eddington limit for black holes. Okay, so key answer number 1, how do supermassive black holes, how do their masses and accretion rates depend on galaxy properties and cosmic time? So the massive black hole galaxy relationship doesn't change that much with redshift, although the accretion rate does significantly increase with redshift. And then the other thing is that the host galaxies and halos for supermassive black holes are growing at about the Eddington rate in the early universe. And so that's why you see those overmassive black holes at that time. So I'll just leave that up as a summary point and then ask if there are general questions.
Well, thank you very much. An excellent talk as always. So there's virtual applause. I find it too awkward to clap at my microphone, so I'll give you the virtual. Mike doesn't. Excellent. So we had some questions, but we have time, lots of time for more questions. Niesh.
Did I raise my hand? I don't think I did.
Oh, maybe it's left over from. Oh, sorry, that's a clap. Sorry, too many hands. Mike.
So what about the stochasticity of the black hole growth and the black hole emission? You know, are they burbling on at a slow and steady rate, or is it short bursts? Is that in principle, I think, should be answerable, I guess, right?
Yes. So in this particular version of the modeling, what we looked at were ensemble properties of black holes, so the distribution of their accretion rates in halos of a given mass, as opposed to following individual black holes through merger trees. And the reason we did that is it's sort of 10,000 times faster to look at the ensemble properties than the individual ones. But our next step is indeed to look at individual black holes in halo merger trees so that we can answer exactly questions like that. We can't really say, does an individual black hole like burble along or have like periods of rapid accretion. All that we can do with this particular modeling is to ask, do we match the overall distribution of accretion rates in galaxies? And now my computer
Yeah, but didn't you have one input datum, which was, I think, the rate of like X-ray to stellar mass ratio? I would have guessed that would give some.
Yeah, so what this does is it tells you for the ensemble population of black holes in galaxies of a given mass, what is the distribution of their accretion rates? But unfortunately, it doesn't let you say for a single black hole, if you go back in time, how is its accretion rate correlated?
Okay.
We can get some information about that by, say, looking at cross-correlation functions between accreting black holes and their surroundings, and correlating for the galaxies where we can measure the star formation rates, because we have somewhat more of a handle on how the star formation rates evolve with time, and so that might tell us how the black hole accretion rates evolve with time. But that's something that we haven't done yet. So we've just looked at the very basic thing, what is the distribution of accretion rates, and not how long a black hole hangs on to a given accretion rate before it moves to a new one.
Okay.
But you said you are going to look at that next. So
yes.
How do you tackle the factor of 10,000?
Yes. So we just have to eat it. So these models take around, let's say, I'm just trying to estimate, around 2,000-ish CPU hours. And so you multiply that by a factor of 10,000 and you gain a little bit because you can use, in some cases, a more efficient algorithm for searching. And you end up with a few million CPU hours. And it's doable, but it's not something that you want to do to start with.
Yeah, I understand.
So when you mentioned that they grow at the Eddington rate and they can grow quickly enough, are you assuming that these are Schwarzschild holes? There's no spin, which can affect things quite dramatically in terms of their growth.
Oh, that's a great question. Yeah. So yes, so if you have a rapidly spinning black hole, that could give you a radiative efficiency of about 0.4, which would mean instead of 50 million years, you'd have to sort of multiply that by 4-ish and get 200 million years, and that would be a big problem. On the other hand, if you had a high spin black hole, you would expect that it wouldn't have spherical accretion. And so the underlying argument for the Eddington ratio, or Eddington limit being what it is, would also be problematic because you would have accretion in a disk as opposed to spherically symmetric. And depending on how thick that disk is, you could get very different answers for what is the e-folding time for that black hole.
Right. But can you given the the phenomenological nature of your model, are you inferring that black holes probably aren't spinning very rapidly? In other words, can you draw that conclusion based on present day data using your models that in all likelihood they haven't been spun up significantly very early on?
Great. So we can only do that if you trust the active black hole mass functions. So if you trust the active black hole mass functions, then we can tell you how the radiative efficiency changes with time. And so let me see, that I thought was a plot that I included here. Where did it go? Where did it go? Oops, not that. Oh, here. Yeah, so if you accept the active black hole mass functions are correct, then the radiative efficiency doesn't change a lot with time. And in particular, it doesn't go up to the levels that you would associate with rapidly spinning black holes.
Right. Yep.
If the active black hole mass functions are wrong by a factor of 3 or more, then you can get up into those territories. And that's certainly a plausible conclusion too.
So Schwarzschild is like 6%, is that right?
Yeah, so it depends, but somewhere on the order of, I think was the minimum, like 3-4-ish% that you could get.
I see.
All right, we are at 12:30. Unless there's a burning question, I would like to end on time. But thank you very much again, Peter, for an excellent talk and sharing this enjoyable work with us. So I'll give one last round of applause, and thanks again for joining us.
Thanks very much.
Thank you.
Thanks to all of you so much.
Very nice.
Have a safe trip home.
Thank you.
All right.
Enjoy your virtual pizza.
Right.
Take
Bye
care.
for now.